Swayam Prabha. Digital India. Educated India.
In the previous lecture, we discussed about SISO, that is single input, single output system, in which one excitation is on the single degree freedom system and there is one output, and for that we obtain the necessary relationships, and in that also we discussed several things like what is the relationship that exists between the power spectral density function of velocity with the power spectral density function of displacement, then power spectral density of acceleration with power spectral density function of displacement, and so on. Now, before we start the multi-degree of freedom system, in which we will have a number of inputs to the system and there will be a number of outputs to the from the system, and the inputs would be represented in terms of a vector and outputs will be also a vector, and as we discussed last time, when you have a number of random processes in a particular vector, then the process is described with the help of the power spectral density function matrix rather than a single power spectral density function. Let us try to recapitulate some of those fundamental things that we discussed in yesterday's lecture, so that we can effectively understand the MDOF system subjected to a random excitation vector. First thing that we discussed yesterday was y is equal to a into x, where y is a vector, x is a vector, and it is connected through a matrix A. In that case, SYY will be a power spectral density function matrix and SXX is the power spectral density function matrix. SYY will be related to SXX with the help of this equation. SXY, that is the cross power spectral density function between the output and input, that is SXY will be equal to A into SXX. Now, if we consider a multi-degree freedom system, then we can write down the equation of motion, and if PT is the excitation vector, then one can obtain the relationship between the frequency contents of the response vector to the frequency content of the excitation with the help of a FRF, that is frequency response function matrix H omega, and this H omega is equal to k minus m omega square plus I c omega inverse of that. That is what we discussed yesterday. Therefore, x omega can be written as x omega equal to H omega multiplied by p omega, where p omega is the frequency contents of the force vector Pt. In case of single degree of freedom system, this H omega matrix is written as small h omega, that is a single quantity which is called also the FRF, that is frequency response function of a single degree freedom system. Now SXX and SYY, these matrices, say for example if it is a vector of size 2, then this will be the nature of the power spectral density function matrix. The diagonal terms are the power spectral density functions of x1 and x2, and the off diagonal terms would represent the cross power spectral density function between x2 and x1, and this will be between x1 and x2. If we have a more number of elements in the vector, then obviously we will have x1, x1, x2, x1, x3, x1, so on. This will be the cross power spectral density function between different responses. And this relationship also was shown, that is x1, x2 cross power spectral density function between x1 and x2 is equal to the complex conjugate of the cross power spectral density function between x2 and x1. In case of the matrix, that means if it is not a single power spectral density function, if this is a matrix, then the relationship is S x1 x2 will be equal to x x2 x1 complex conjugate and transpose of that. So that is the difference between the single quantity as the cross power spectral density function and the Sx1 Sx2 or the cross power spectral density function and between x1 and x2. In that case, x1 and x2 will be the two vectors. Now, the diagonal terms of the power spectral density function matrix are real, and they are frequency dependent, and generally we do not write omega in front of it, but it is understood that for each frequency we have a matrix like this. Therefore, as we go on varying the frequency, then we have for each frequency one matrix like this. Now, with the help of this, we would now go into the multi-degree of freedom system, and in the previous lecture also we had shown that x omega is equal to h omega into p omega, that they are all complex numbers. P omega is obtained from first Fourier transform, and Sxx, the power spectral density function of the response, is equal to absolute value square of h omega into the power spectral density function of p. Now, this can also be written as h omega into SPP into h omega star, because this multiplied by this becomes equal to the absolute value square. And the cross power spectral density between the response between the force and the response is equal to h omega SPP. Apart from that, we also had proved in the previous lecture that the power spectral density function of velocity is equal to omega times the power spectral density function of displacement, and power spectral density function of acceleration is equal to omega to the power 4 into the power spectral density function of displacement. Now, in case when this x dot and x they are vectors, then they are matrices, and the power spectral density matrix of velocity is related to the power spectral density function of displacement, again through this relationship, only thing that this changes to matrices. Also we had proved that Sx dot plus Sx dot x is equal to 0, that is the cross power spectral density function between the velocity and displacement, that if it comes into the solution or analysis, then the we ignore that, means we set that to equal to 0 because of this reason. Similarly, if the velocity and acceleration, for that if we have a cross power spectral density function or cross power spectral density matrix, then we ignore that because of this reason, that this plus this, that becomes equal to 0. And also we had seen that Sxy is equal to Syx star t, that is the complex conjugate of this and transpose of that. So with these few things that we described in the previous lecture, we come into the response of a multi-degree freedom system excited by a force vector Pt. Now for single point excitation, we know that the force vector Pt is equal to minus m into I into x double dot g, where I is a influence coefficient vector consisting of 1 1 1 or 1 0 1 0 1 0 and so on, that you have seen in the case of the deterministic analysis. X omega we can write down to be equal to H omega matrix multiplied by P omega, that is what we have just discussed, where H omega is the power, frequency response function matrix for the system, multi-degree of freedom system, and P omega is the frequency content vector of the excitation Pt, and X omega is the frequency contents of the response. Now if this relationship holds good, then from the just discussion that we had, from that we can write down the power spectral density function of Sxx, that is the power spectral density function matrix of x is equal to H omega matrix multiplied by the SPP matrix, that is the power spectral density function of the excitation, into H omega star t. In the case of the single degree freedom system, if you recall, we had we could write it as small h omega multiplied by SPP multiplied by small h omega star, and h omega star, small h omega star, and this h omega if we multiply, that becomes the absolute value square of h omega square. If h omega is a matrix, then we have to make it a transpose of the complex conjugate of the matrix h omega. So then only it will become the absolute value square. So this is a standard relationship that we use for the case of a multi-degree of freedom system. What you have to simply do is that you have to find out the FRF, that is the frequency response function matrix for the system, which is equal to k minus m omega square plus I c omega, and inverse of this matrix if you take at every frequency, then you get h omega at every frequency, and SPP at every frequency is known, So, you have to carry out this matrix multiplication, and from that you will get the value of the power spectral density function matrix at each value of omega. Now, in case of the single point excitation system, SPP, that turns out to be MI into IT MT into X Sx double dot G, and these follows from this relationship, that is Pt is equal to minus Mi x double dot G, and therefore, if we wish to write down the value of SPP, then it will be Mi into Sx double dot G multiplied by the IT MT, that is A Sx AT, that what we have discussed just now. So, using that one can write down the SPP, that is it will be Mi into ITMT. In place of writing ITMT on this side, we have taken it on this side, because Sx double dot G is a single quantity in the case of the single point excitation. So, therefore, whether we keep ITMT on this side of Sx double dot G or in this side, it does not matter. Now, with the help of this relationship that we obtain for SPP, the SXX, that is power spectral density function matrix of the response, can be written in this particular form, that is HM I, then ITMT H star T into X double dot G, where X double dot G is the power spectral density function of the ground motion. So, it is a single quantity at each frequency, and the cross power spectral density function between the ground acceleration and the displacement, that will be equal to minus H M I x double dot G, and that follows from the equation that again we just examined, that is Sx output input correlation is equal to A into Sx. So, in place of A we write down here now HMI. So, that becomes the pre-multiplier for the Sx double dot G. Now, using these relationships, a problem is solved, and this problem was the problem in which we had two responses at the or non-support degrees of responses. The problem is I think the problem is, this was the problem, and that is we had U1 and U2 as the displacements, and we had three ground excitations, and in this case all the three ground excitations are assumed to be the same, and therefore we had a R matrix, that is in place of R matrix we had only a I matrix. So, so this is the I matrix. You can see here the I matrix is equal to I 1 1, that this is because of the fact that the ground excitations at the three supports are assumed to be the same, they are not different. Therefore, the I influence coefficient vector will be equal to 1 and 1. So, we know the mass matrix, we can construct the C matrix from the relationship that is alpha m plus beta k, and alpha and beta can be obtained from the two frequencies that you have obtained. So, with the help of that, the alpha value had become 0.816 and the beta value is 0.0027. This is the K matrix, and from there we can obtain for each frequency the H matrix, that is by inverting this matrix, and obtain the value of the power spectral density function matrix of the two displacements using the previous equation. And the diagonal terms of the power spectral density function matrix, that is the PSDFs of the two displacements. So, that is what is shown here in the plot. You can see that it is the power spectral density function ordinates for displacement u1, and this is the frequency, and that is how the PSDF of the displacement u1 varies with frequency, and one can see that this is peaking nearly at about 12.5, and the first frequency of the system is 12.25. So, therefore, we see that there is a the peak of the power spectral density function of displacement u1 is around that frequency. This is the power spectral density function of the displacement u2. These area under the curve of this power spectral density function of u1 and u2, they provide the variance, and the square root of variance gives the standard deviation of the displacement, and in case of zero mean process, the standard deviation is equal to the root mean square value. So, the root mean square value of u1 is 0.0154 and the root mean square value of the displacement and 2 or u2 is 0.0078. Now, when we consider the multi-point excitation system, then the this is SXX, this is not SX double dot G, it is wrongly written over here. It will be SXX, that is the power spectral density function of matrix of the response, is equal to now H m in place of R. Now, we have in place of I we have got now R. So, H m R, X double dot G is a matrix now, is not a single quantity, because the size of the matrix would depend upon the number of the point of excitations, and it is multiplied on the right hand side by R t, M t and H star t. So, that is the general relationship between the displacement and the excitation. Displacement is a vector, the force is a vector, and therefore, the this is a matrix of displacement, and this is a matrix of the or power spectral density function matrix of excitation, and R is the influence coefficient matrix that we had discussed when we are solving the problem for the multi-degree of freedom system subjected to the deterministic ground motions which cause different excitations at different supports because of the time lag. Sx double dot Gx, that is the cross power spectral density between the excitation and the displacement is given by this expression again, and here Sx double dot G again is a matrix. The size of this Sx double dot G matrix is S into S, if S is the number of support and R is a influence coefficient matrix that is obtained from a static analysis of the system that we have seen before, is of the size of n into S. That is, if there are n degrees of freedom and if there are S number of support excitation, then the displacements that will be caused at the n non-support degrees of freedom, that will be represented by a matrix n into S. Many a time we are not interested in all the response quantities, say only a limited number of response quantities may be involved. For example, in this problem we consider that this is a frame subjected to two ground excitations, different ground excitations arising because of the time lag, and there are 5 degrees of freedom in the system, that is non-support degrees of freedom. Then H omega matrix will be equal to a 5 by 5 matrix. Now say we are interested in only the response x1 and x4. In that case, we can have a reduced frequency response function matrix, which will be called H bar omega, equal to 2 by 5. That is, we can select the first row and the fourth row and make a modified H omega matrix called H bar omega matrix, and its size will be equal to 2 into 5. Now Sxx now will be a 2 by 2 matrix, because we are only interested in the responses x1 and x4. So the diagonal terms of these matrix would give you the power spectral density function of 1 and 4, and the off diagonal terms will give the cross power spectral density function between 1 and 4 and 4 and 1. So that is what the Sxx matrix will represent, and it has the same equation as that of 4.77 that we had just discussed, that is H m r Sx double dot G, then R t m t H star t. Only in place of H star and H, we write now H bar and H bar star, where H bar is this modified frequency response function matrix. And if we put the sizes of different matrices here, we can see that this finally leads to, this multiplication finally leads to a 2 by 2 matrix, which will be the size of the matrix Sxx. So in many problems, what we do is that we may not be interested in all the displacements or all the response quantities, and for that we take a reduced frequency response function matrix and use the same equation that we have stated over here with the help of equation 4.77. Now the equations that I had shown before or in the previous slides, they have been obtained or derived with the assumption of ergodicity, and that we did purposefully because it is easy to understand this relationship by assuming the stationary process to be ergodic, because in that case we will be dealing with only one time history, and with the help of the Fourier transform of that we can construct all that relationship. However, all the relationship that we have derived in the previous slide, they can be also derived without the assumption of ergodicity, that is by assuming the process to be a stationary random process, and in that case what we will do is that we will start with the autocorrelation and cross correlation functions of the process or of the two processes, and then take a Fourier transform of them, and using that we would come to all the equations that you have derived before. And we had seen before that there exists a relationship between the autocorrelation function and the power spectral density function through a Fourier transform pair. Now, let us solve a problem of multi-degree or multi-point excitation system, that is example 4.2. If a time lag of 5 seconds is introduced between the supports, find the PSDF of U1 and U2. That is the problem. This problem. In this problem, we can now assume that the x double dot g1, x double dot g2 and x double dot g3 are different, and there is a time lag of the 5 seconds between these excitations. So, the time lag between x double dot g1 and x double dot g3 is 10 seconds, x double dot g1 and x double dot g2 is 5 seconds, and x double dot g2 and x double dot g3 is 5 seconds. So, these are the time lags. Then first we have to construct Sx double dot G matrix, that will be a 3 by 3 matrix of the ground motion, and the diagonals of this would be the power spectral density function of the excitations at this point, at this point and at this point, and the cross power spectral density functions would represent the cross power spectral density function between this excitation and this excitation, and so on. So, this is the Sx double dot G matrix, a 3 by 3 matrix. So, if we have to construct that matrix, then let us recapitulate what we discussed in the seismic input part of our study. In the seismic input, if you recall, we discussed about a coherence function, and one of the empirical equation of the coherence function, which is a very simple one, is this, that is exponential of minus absolute value of Rij into omega divided by Vs, where Rij is the distance between the point I and j, that is at these 2 points we have excitations, and the distance between these is Rij. The Vs is the seismic wave velocity. So, the same earthquake train or ground motion or time history of ground motion that is travelling with a velocity of Vs. In that case, one can replace Rij by Vs by the phase or the time lag, that is Rij divided by Vs is equal to the specified time lag. That is the time that will be required to travel from I to j if the velocity is Vs. Now, this has been specified, that is between the supports the time lag is 5 seconds. So, in this we can replace this quantity Rij by Vs by 5. Now, once we have done that, then coherence function between the first support and the third support will be equal to exponential of minus this quantity will be 10 second into omega. Similarly, between the support 1 and 2, that is this support between 1 and 2, you will have 5 second, that means Rij by Vs will be replaced by 5 second, and x double dot G2 X will be again by 5 second. So, one can construct the matrix easily, because the cross power spectral density functions between the supports are now known. This cross power spectral density function is given by this equation. If we recall the seismic input that we discussed, and this is the power spectral density function at support I, and this is at support j, and it will be multiplied by a coherence function COH I comma j. And since this is known now, one can obtain the different cross power spectral density function very easily. In the case of a single earthquake ground motion, train of ground motion moving with a velocity, the power spectral density function at different supports remains the same, that is equal to Sx double dot g, that is which is specified. Only the change or the cross power spectral density function arises because of the coherence function. So, we write down the cross power spectral density function between the two excitations I and j as coherence I comma j into Sx double dot g. So, in this particular fashion, one can write down all the cross power spectral density function terms. Note that Sx double dot g and x double dot gi, that is the cross power spectral density function between j and I, is equal to cross power spectral density function between I and j. This happens in this case because Sx double dot g is a real quantity. There is no complex quantity involved over here, and since they are real quantity, the star that you had used in defining the relationship between the cross power spectral density function between point 1 and 2 and point 2 and 1, that star is not required, and therefore, they become the same. Now, with the help of that, we obtained the power spectral density function matrix of excitation, that is given by this matrix. The R matrix we had computed before for this problem. The R matrix was 1 by 3 into 1 1 1, and this coherence function we have used. Sorry, in the previous discussion I have simply written it as Vs. It will be 2 pi by Vs, and the values of rho 1 and rho 2, they are 5 omega by 2 pi and 10 omega by 2 pi. So, with that values of rho 1 and rho 2, one can obtain the cross power spectral density function matrix of excitation. So, this is the cross power spectral density function between the support 1 and 2, and this is between support 1 and 3. And we have taken Sx double dot g, a single quantity common out of them, because a single power spectral density function is defined for the ground motion, and the excitations at different points vary because of the phase lag. So, this becomes a power spectral density function matrix, and this is the R matrix. So, therefore, with the help of these and the H matrix, one can obtain the power spectral density function matrix between of U1 and U2, these two displacements, and the diagonal terms of that matrix gives you the PSDFs of U1 and U2. So, they are plotted here, and the plot again shows that the maximum value occurs around the first fundamental frequency of the structure, and the values of the or the RMS values of the responses becomes equal to 0.0089 and 0.0045 for U1 and U2. So, this is the PSDF of U2. The time history analysis that we obtained for the El Centro earthquake, note that the power spectral density function input that you have given here is the power spectral density function of the El Centro earthquake, which is tabulated at the end of the book as an appendix. One can use those digitized values. So, we have used those digitized values for obtaining this the power spectral density function ordinates at different frequencies. So, when we obtained we took the same El Centro earthquake as a time history, and we did a time history analysis for the monthly support excitation system with a time lag of 5 seconds between supports. We obtained the result as 0.0092. So, that was the value of the RMS value of the response that we obtained from the time history, and the spectral analysis give the result at 0.0089. So, you can see that the results are very close to each other. That verifies or validates the accuracy of the result. We solved another problem which was a problem of the pitch roof portal frame, that is we had a pitch roof portal frame, if you recall, and there is a degree of freedom here and a vertical degree of freedom 5, and this is having a multi support excitation, and these multi support excitation here they are two multi support excitations. The time lag between these 2 points is given as 5 seconds, that is Rij by Vs, that becomes equal to 5 seconds. So, one can have a correlation coherence function with rho 1 defined as exponential of minus 5 omega by 2 pi. So, with the help of that we can construct the 2 by 2 power spectral density function of excitation. Sx double dot G again is the power spectral density function of the El Centro earthquake that we have taken, and with the properties of the pitch roof portal frame, that is the mass matrix defined as this and the K matrix defined as this, we obtain the two natural frequencies as 5.58 and 18.91. The alpha and beta that was calculated with the help of these two frequencies were 0.431 and 0.004, and this was the C matrix that you constructed, and the R that you determined before, that is the influence coefficient matrix. So, with these matrices defined, we again used the same equation for finding out the the power spectral density function of displacement 4 and 5, and using that multiplication of AMR and R, M and H omega star so on, we obtained the power spectral density function matrix of the displacement, that was a 2 by 2, and results are compared for the two cases. That is, in one case we assume that it is perfectly correlated, and in other case we assume that there is a phase lag of 5 second. The results which are given over here is not correct. The correct results are shown over here in this paper. That is the RMS value that was worked out for this displacement and this displacement was 0.0331 when it was fully correlated, that is there was no time lag between these 2 points, and when they were partially correlated, that is there was a time lag between the two, the RMS value of the response was 0.023. So, one can see that when there is a for fully correlated ground motion, that is for the single support excitation, the response is more compared to when it is partially correlated. For the displacement 5, when it was perfectly correlated, the value was 0, that is expected, because these two supports would be moving as a single unit, that is it becomes a single point excitation system, and in that case we expect that there will not be a vertical motion over here. The entire thing would be vibrating in this particular fashion, and for when it is partially correlated, so there is a little bit of displacement that occurs at the crown. So, this shows the importance of the correlation between the excitations at the two supports. If we assume it to be perfectly correlated, that is we assume it to be a single point excitation system, then in some cases we can get some erroneous result for certain degrees of freedom. It is better to consider the partial correlation between the excitation produced by the single earthquake traveling at a certain speed. However, this kind of thing needs to be done only for cases where the two supports are spatially separated by a large distance. For small distances, this particular partial correlation, effect of partial correlation is almost negligible. Though the power spectral density function matrices are or the power spectral density function matrices are shown over here, and one can see that the frequencies at which it is peaking is nearly equal to the frequency of the first frequency of the system. Now, here these the power spectral density functions, they differ a little bit for the case of with time lag and without time lag, and that is shown over here. This is with time lag, and for without time lag there was only one peak, whereas with time lag there are two peaks in the power spectral density function. Next, let us come to the absolute displacement, that is how to obtain the power spectral density function of absolute displacements of the responses. Whenever we have a multi-support excitation system, we have seen that there are two displacements that one need to consider, that is a relative displacement of the non-support degrees of freedom with respect to the support, that is called the relative displacement. The other one is the absolute displacement, in which the total displacements at different non-support degrees of freedom are considered. It is necessary because if we wish to find out the member end forces, then we require the relative displacement of one end with respect to the other in terms of the total displacement for a multi-support excitation system. For single support excitation, since the same displacement takes place due to the ground motion at all supports, therefore, it is only the relative displacement that is good enough to obtain the member end forces from the displacement. Now, the absolute displacement can be written with the help of this equation, that is I into x plus r into xg. So, if we look at this expression over here, the I is a matrix of identity matrix, that is diagonal terms are 1 1 1, off diagonal terms are 0, that multiplied by the 3 displacements u, that gives the relative displacements of the system, and the ground displacements are xg1 to xg4, therefore ground displacements, and therefore we have a R matrix which will be 4 by 3 R matrix, and when it will be multiplied by this xg vector, then we will get the influence of these displacements coming on to these non-support degrees of freedom. So, the influence of this at these 3 degrees of freedom plus the displacements that is caused at these 3 points because of the vibration of the structure with respect to the support, that is given by this. Addition of these two becomes the absolute displacement or the total displacement. Now, once we have these equation, then using that equation one can write down the power spectral density function matrix of absolute displacement with the help of this equation. This becomes Sxx itself, because this is an identity matrix, and therefore, the I and IT of that, if I multiply with Sxx, it remains Sxx itself. This becomes R into Sx double dot G into RT, then S x x double dot G, that becomes, or xg, that becomes equal to I Sxg RT, and Sxgx, that becomes into R into Sxgx IT. Now, what is not known to us, this is known to us, Sxx is known to us from the dynamic analysis of the system. Sxg, that is also known because we know the power spectral density function matrix of the ground acceleration, and from that power spectral density function of ground acceleration, one can find out the power spectral density function of the displacement. This relationship we had shown before, that is Sx double dot G is equal to omega to the power 4 into Sxg. So, there exists a relationship between the power spectral density function of ground acceleration and the ground displacement. So, using that relationship one can find out Sxg if Sx double dot g is specified. Now, here this is the term cross power spectral density function between the response, that is the displacement, and the ground displacement that is to be obtained, and once this is known, this Sx A matrix is completely known. Now, one can write down the relationship between the xg and x from the relationship that exists between these, that is Sx omega is equal to minus h m r x double dot g omega. So, this is a basic equation that we write. If we recall, for the single degree of freedom system, we had written x omega is equal to h omega multiplied by p omega. Okay. Now, here the p omega is equal to m into r, and h is the H matrix. So, x omega vector is related to x double dot g vector, that is the ground acceleration vector, with the help of this relationship, and once we have this relationship, then x double dot g omega further can be written as omega square multiplied by x g omega. That follows from the relationship, basic relationship that exists between the ground displacement and ground excitation if they are assumed to be a harmonic excitation. And for harmonic excitation, whether we represent it in the complex form or in the real form, we know that the displacement and the acceleration are related through omega square. So, that is why this x double dot g omega is replaced by omega square into x g omega. And once we have this relationship, that means this is equal to this x omega, then from this I can easily get the cross power spectral density function between x g and x and x g. So, here it will be, of course, there will be a, since it is a matrix, there will be a complex conjugate of transpose. So, that star is missing over here. So, with the help of these relationships, that is, once we know Sx g x and Sx g, then one can obtain the value of the power spectral density function matrix of the absolute displacement. So, we stop at this, we will solve a problem in the next class.